everybody. So we've already seen a number of different strategies of writing this alternating function. And now what I'm going to demonstrate is that the method we use that makes use of NumPy is going to be way faster than basically the version that uses lists. So let's start by remembering what we did for the NumPy one. So I'm still in the same Jupyter session, so you might need to re-import NumPy if you've kind of closed Jupyter and come back, but mine is still going, so I don't need to re-import it. And remember here, okay, so we had Alt3, and we said A is, we create an array of zeros, and then we add 3, and then we change all of the odd indices to be 7. So that's great. What I'm going to do now is I'm going to write a function called Alt4, and it's going to try to mimic this Alt3 function as closely as possible, just without using NumPy. So we're going to be using lists. So let's say def Alt4 of n. And okay, so the first thing that Alt3 does is it creates this 1 by n row vector, and then it adds 3 to everything. So it kind of has it's this constant list. So let's start by initializing an empty list, my list. And we're going to say for I in range of n, let's take my list and append 3. So what this does is it mimics this line of code, so that's good. So what we need to do now is just change the odd indices. So now let's say for I in range, let's start at 1. It's a length n vector, so I can't go past n anyway. And let's count by 2's. What I want to do is say my list of I is equal to 7. So that mimics this line of code where we're changing all of the odd indices to be 7. So what's missing from this function is, well, I need to return my list. So I don't want to return it in this for loop. I don't want to return it in this for loop. I need to return it after I've been through both of the for loops. So here, let's return my list. And let's see what's going on here. Oops, what did I do? I used parentheses instead of square brackets for indexing. All right, so now this looks good. And let's test it out. So I can say Alt4 of, let's say, 10. That looks good. Let's try it with an odd index or input. Let's try 11. Oops, and Alt4. And let's see, 3, 6, 9, 10, 11. That looks good as well. All right, so Alt4 is working how we expect, and it kind of works in pretty much the same way as Alt3, just without using NumPy. So, okay, like I said, we're now going to be timing these strategies. So I'm going to show you just how much faster using NumPy is. But first thing is, the only thing we've seen so far for timing is using the Jupyter Magic time it. So I could say time it, and I could say then, like, let's just say Alt4 of 10, and I can run it. So we can see here it took 1.3 second microseconds, so that's 10 to the negative 6. And I don't think we've seen the microseconds before, so here's just an example of it. So we've seen milliseconds, so 10 to the negative 3, nanoseconds, 10 to the negative 9, and now microseconds, 10 to the negative 6. But the issue with time it is, okay, so it like returns this statement, but the issue is how do we extract this 1.37 microseconds? That's what we really care about. So I'm going to show you a slightly different way of doing it. And what we're going to need to do is import time. Now, this isn't something you need to install. It's already going to be on your computer. So now I'm just going to run it. And what I can do is I can say time.time. And what this does is return the amount of time elapsed since, I believe, January 1st, 1970. So that's kind of considered the start of time in kind of computer land. It's not very important what it represents for us, but you can just think about this as some measure of time. And then what I can do now is I can say, well, time.time again. And we can see here that we went from 39 to 61. So that's the time elapsed since I've been talking and running the commands. So let me show you how we can kind of use this strategy to measure how long it takes for Alt4 to run. So for instance, I can say start equals time.time. then what I can do is I can run Alt 4 of, let's just say 10 to the power of 3. Remember, to get exponent, I use double stars. Then I can say, let's say end is equal to time dot time. And then if I wanted to get, well, how long did it take? I can say, well, t is equal to end minus start. And I can run this, and I can see, well, what is t? And we can see here, well, it's 0.0002. So, okay. Using this strategy, I now want to introduce while loops in Python. So we've seen for loops, logic, all of that stuff. So all of the things that we built up to in MATLAB, we now more or less know how to do in Python. But I haven't shown you the syntax for a while loop, so let's see how to do it. And the idea here is I want to find an input from my function alt4. So I want to find a number n where it takes more than 5 seconds for us to run alt4 of n. So the way I'm going to do that is I'm going to start by initializing our time t to be equal to 0. And what I'm going to do is say, okay, while t is less than 5, and let's also initialize, sorry, n equal to 100. Now I'm going to say, okay, so while the time is less than 5, I'm going to increase n by, or I'm going to multiply n by 2. I'm recording this video. I know what happens if you try it with larger numbers, and it slows down significantly. So multiplying n by 2 every iteration is a pretty good one to pick. And what I'm going to do next is I'm going to say, okay, let's copy paste the code that we wrote above. So I'm going to start the timer. I'm going to run my function alt4. And what should I change here? Instead of having it be 10 to the 3, I should just have it be n. Then I'm going to stop the clock, and then I'm going to say, okay, how long did it take? Now, one thing that you might be wondering is, well, can we increment n underneath? And the issue with that is, so notice, okay, let's say t is less than 5, so maybe it's like 4.9 seconds. I enter. Now let's say I double n, and it takes like 5.7 seconds or something like that. So then I won't enter the while loop again, and the value of n that's stored is the one that, it's the first one that takes longer than 5 seconds. If I increment n underneath here, so let's say n equals 5.7 seconds for this n, and then or it enters and it takes that time. If I increment it at the bottom, then it's going to not give me the first n that jumps above 5 seconds. So that's why it needs to be incremented here. So, okay, oops, let's run this. And I might fast forward the video depending on how long it takes. So it looks like it's taking a little bit of time, so I'll see you in the future. All right, we're back. I didn't actually end up having to fast forward, but yeah, it's the future still. Okay. So now let's see what was t. And we saw here, okay, t was 5.36 seconds. That looks good. And let's see, well, what was n? And we can see here, let's see, is that 52,428,800. So, okay, took 5.36 seconds. That was with our alt4 function. Now let's see how long it takes for alt3. So this is our NumPy optimized one. So let's see what happens. So what I'm going to do is I'm going to say, I'm going to keep the timer the same. And instead of having alt3 of n, I'm just going to, or alt4, I'm going to have alt3. Let's also just print n so we can remind ourselves that we really are working with the same one. Let's print the time. And let's see what happens. So we can see here, yep, that's the same value of n. But notice now it took less than half a second to run. So if you ask me, that's pretty impressive. So this alt3 function that used NumPy was significantly faster than the list version. So just for comparison again, here's alt3. Remember, alt4 was written to work in basically the same way, just using lists. So pretty cool if you ask me. You might be wondering, okay, well, the alt3, remember, this returns a NumPy array, and this returns a list. So let's see what happens if we try to convert A to a list. So let's do the same thing. What I'm going to do is copy paste this function, but I'm going to call it alt3a because we're going to do a couple different versions. So let's run this. Now I'm going to copy paste the same timing code, but now just alt3a. And I didn't actually change this function. What I'm going to do is let's convert the numpy array to a list. So let's run it. And you can see it's still running, and okay, now it's printed t. So now it takes 3.74 seconds. So it's still less than 5 seconds, but it's nowhere near as fast as this less than half a second that we got when we just had no lists involved. So we can see here conversion to the list really did slow things down. So we can save a lot of time by not converting to a list. So what's the takeaway of that is that unless you really need a list, maybe don't do the conversion. So let's see, another thing that we can do is, let's see, so I'm going to keep, let's see, oops, that's not what I wanted to copy paste. I want to copy paste the original alt3 code again, so let me go grab it. So what if instead now, so I'm going to call this alt3b. So, okay, what if instead of doing this slicing and reassignment, what if instead we did a for loop? So now I said for I in range, let's go 1, don't go past n, also don't include n, go up by 2. And now let's say a of I is equal to 7. So I'm going to save this. Let's time it now. Oops. All right, so notice what's different now is we're using a for loop. And let's time it and see what happens. So we can see we're still using the same n, but the star here means I'm waiting. And we can see here 3.86 seconds, so even slower than before. So what's the takeaway from this example is that for loops in general are pretty slow. So if you can avoid using them and if you can make use of NumPy, then that's a really good thing to do. You can really speed up what you're trying to do by avoiding these for loops and by using NumPy as much as possible. So I think this is a good place to end the video. Thank you for watching, and I will see you in the next one.